Have you ever wondered if time could loop in on itself, creating an endless cycle of universal death and rebirth? This seemingly fantastical concept isn't confined to the realm of science fiction, but is a legitimate area of study in cosmology, known as cyclic universe theory. In a nutshell, cyclic universe theory proposes that our universe is part of an infinite series of expansions and contractions, or births and deaths. This implies a radically different understanding of time, one where time doesn't simply move forward in a straight line, but rather cycles back on itself in a grand cosmic loop. This isn't a new idea. In fact, the concept of a cyclic universe has a long and storied history. Ancient cultures such as the Mayans and Hindus believed in cyclical time, where the universe underwent repeated cycles of creation and destruction. These beliefs were largely dismissed with the advent of modern science, but the idea was revived in the 20th century with the development of new theories in physics and cosmology. The evolution of cyclic universe models over time has been quite remarkable. What started as philosophical and religious musings has transformed into complex mathematical models, grounded in our understanding of physics. These models have been refined and expanded upon, incorporating new discoveries and addressing various challenges and criticisms. However, the study of cyclic universe theory is not without its controversies. The theory challenges our fundamental understanding of the universe and time, and many questions remain. How does the universe transition from expansion to contraction and vice versa? What happens to matter and information across cycles? And perhaps most importantly, how can we test these theories? These are not easy questions to answer, but they are the kind of questions that push the boundaries of our knowledge and understanding, that force us to reassess our assumptions and beliefs, and that ultimately drive scientific progress. If this question intrigues you, then join us in exploring the fascinating theory of a cyclic universe. The journey won't be easy, but it promises to be a thrilling ride, filled with unexpected twists and turns, and perhaps even a few paradigm-shifting revelations. So sit back, buckle up, and let's dive into the wonders of the cyclic universe. The cyclic universe theory isn't a singular idea, but a collection of models, each with its unique propositions. Let's delve into three such models: the Big Crunch, Big Bang, conformal cyclic cosmology, and ekpyrotic models. The Big Crunch, Big Bang model is like a cosmic heartbeat. It proposes that our universe began with the Big Bang, expands for a time, then contracts in a big crunch, only to bang again. This contraction and expansion is a cyclic event, with each cycle potentially lasting billions of years. Next, let's explore conformal cyclic cosmology, or CCC, invented by Sir Roger Penrose. This model suggests that each cycle of the universe lasts infinitely long. In this model, as one universe eon expands and cools, it becomes indistinguishable from the Big Bang of the next eon. A key feature of CCC is the smoothness of the transition from one eon to the next, with only the most persistent gravitational waves making the leap. Finally, there's the ekpyrotic model. It's a bit of an outlier derived from string theory. The idea here is that our three-dimensional universe is a brane or membrane floating in a higher dimensional space. The cycle in this model comes from periodic collisions between our brane and another, sparking off Big Bang-like conditions. Each of these models has its own unique mechanism for transitioning between cycles. The Big Crunch, Big Bang model relies on gravity eventually overcoming the current expansion of the universe, causing it to collapse and bang again. CCC, on the other hand, relies on the universe expanding and cooling indefinitely until it smoothly transitions into the next cycle. The ekpyrotic model's transition is a little more dramatic, involving a collision in higher dimensional space. While these models differ in details, they share the core idea of a universe rebirthing from its own ashes. So, whether it's a cosmic heartbeat, an infinite series of eons, or a clash of branes in a higher dimensional space, these cyclic models all aim to explain the past, present, and future of our universe. So why do scientists propose these cyclic models? What limitations of the standard Big Bang model do they address? Well, let's delve into it. The standard Big Bang model, while widely accepted, does have some limitations. One of the key challenges is reconciling the concept of cosmic inflation with our observations of the universe. Cosmic inflation is the theory that the universe expanded at an astronomical rate in just a fraction of a second after the Big Bang. But while this theory explains a lot, like the uniformity of the cosmic microwave background radiation, it also raises some big questions. For instance, why did inflation start and stop when it did? And why is the universe so flat and evenly distributed? This is where cyclic models come into play. These models propose that the universe didn't just inflate once, but goes through regular cycles of expansion and contraction. This could explain why inflation started and stopped when it did, and also why the universe is so flat and evenly distributed. In essence, each cycle smooths out the universe a little more, making it flatter and more uniform with each pass. Moreover, cyclic models address the question of what happened before the Big Bang. The standard Big Bang theory struggles to answer this, as it essentially posits that time and space began with the Big Bang. But in a cyclic model, the Big Bang is just one of many points in a never-ending cycle of expansion and contraction. This provides a potential answer to the question of what came before the Big Bang, another cycle of the universe. Finally, cyclic models also tackle the problem of dark energy. In the standard Big Bang model, dark energy is causing the universe to expand at an accelerating rate. But if this continues indefinitely, the universe will eventually become a cold and empty place. Cyclic models, however, propose that the universe will eventually contract, leading to a new Big Bang and a fresh cycle of expansion. These cyclic models offer potential solutions to some of the most puzzling questions about our universe. Now that we understand why scientists propose cyclic models, let's delve into the key aspects of a cyclic universe. One of the most intriguing elements of the cyclic universe is the concept of the bounce. This is the pivotal moment when the universe transitions from expansion to contraction, and vice versa. It's akin to a cosmic inhalation and exhalation, a rhythmic cycle of growth and retreat. The mechanisms that drive this bounce are still under investigation, but theories point to the roles of dark energy and dark matter. These unseen entities, though elusive, are thought to account for over 95% of the universe's total mass energy content, making them critical players in the cosmic dance. Of course, this raises questions about the fate of information and matter. Do they endure across cycles, or are they reborn in some way? This is a hot topic in physics, as it touches upon the fundamental laws of conservation. Some theories suggest that information may be reset with each bounce, while others propose that matter and energy may undergo a process of transformation, persisting in altered forms. These possibilities have profound implications for our understanding of identity and continuity. Lastly, we need to consider the testability and observational constraints of these models. After all, science is about evidence. While cyclic models are mathematically elegant, proving them empirically is another matter. We're looking for signs of previous cycles, echoes, if you will, in the cosmic microwave background radiation, the oldest light in the universe. We're also exploring gravitational waves, ripples in the fabric of space-time for clues. These are early days and the hunt is on, but the answers could revolutionize our understanding of the universe. These aspects provide the backbone of the cyclic universe theory, shaping our understanding of the universe's past, present, and future. While the cyclic universe theory is fascinating, it's not without its mysteries and challenges. In the realm of cosmic inflation, cyclic models face a unique set of hurdles. Inflation is a key component of the standard cosmological model, explaining the uniformity and flatness of the observable universe. In the cyclic universe, however, this inflation needs to be incorporated in a way that allows for repeated cycles of expansion and contraction. Achieving this in a mathematically consistent manner is no small feat, and it remains a topic of ongoing research. Quantum mechanics and string theory also play vital roles in our understanding of the cyclic universe. Quantum mechanics, with its inherent probabilities and uncertainties, might provide clues about the nature of the bounce, the transition from contraction to expansion. Meanwhile, string theory, with its extra dimensions and branes, offers a framework that could potentially explain the cyclic behavior of the universe. However, integrating these theories into the cyclic model is a complex task. The quantum scale and the cosmological scale are vastly different, and unifying them is one of the greatest challenges in theoretical physics. But beyond the scientific and mathematical complexities, the cyclic universe theory also presents profound philosophical implications. If the universe is cyclical, what does this mean for our understanding of time, existence, and the meaning of life itself? Does time have a beginning or an end in a universe that is constantly cycling? And if matter and information persist across cycles, does this challenge our understanding of identity and continuity? These questions delve into the deepest realms of philosophy, adding another layer of richness to the cyclic universe theory. These open questions push the boundaries of our understanding, driving us to explore deeper into the cyclic universe theory. While the cyclic universe theory offers intriguing possibilities, it's important to consider its criticisms and alternatives. One of the main criticisms of cyclic models is the lack of direct observational evidence. While these models offer elegant mathematical frameworks and can potentially address some limitations of the standard Big Bang model, they are ultimately hypotheses. Until we have concrete evidence to support them, they remain in the realm of speculation. Another criticism is the complexity of the mathematical framework required for these models. The equations and concepts used in cyclical models are often far from straightforward, requiring advanced understanding of physics and mathematics. This complexity can make it difficult to communicate these ideas to a wider audience, limiting the overall understanding and acceptance of these models. Moreover, the cyclic universe theory faces challenges when it comes to the conservation of energy and entropy. The universe's entropy, or disorder, increases with each cycle, creating a so-called entropy problem. If the universe has existed for an infinite number of cycles, why isn't the entropy infinitely high? Now, let's consider some alternative explanations for the ultimate fate of the universe. One such alternative is the heat death scenario, which suggests that the universe will continue expanding forever, gradually cooling as it does so until it reaches a state of maximum entropy. This scenario is often seen as more straightforward and has more observational evidence to support it. Another alternative is the Big Rip scenario, where the universe's expansion accelerates to the point that all matter and structures are torn apart. This theory is based on the assumption that dark energy, the mysterious force driving the universe's expansion, will continue to increase over time. Yet another possibility is the Big Crunch, where the universe eventually stops expanding and starts contracting, leading to a hot, dense state. This could potentially lead to another Big Bang, creating a cyclic universe and bringing us full circle back to the cyclic models. By considering different perspectives, we gain a more balanced and comprehensive understanding of our universe. In this journey through the cyclic universe theory, we've explored a realm where time can loop and universes can be reborn. We've delved into various cyclic models, peering into the Big Crunch, Big Bang, the conformal cyclic cosmology, and the ekpyrotic models, each proposing unique mechanisms for the transition between cosmic cycles. We've pondered over the motivation behind these models, the limitations of the standard Big Bang theory, and how cyclic models strive to address these challenges. We've grappled with the nature of the bounce, the fate of information and matter, and the testability of these intriguing models. From cosmic inflation to the role of quantum mechanics and string theory, we've navigated advanced topics and open questions. And we've acknowledged criticisms while considering alternative explanations for the universe's ultimate fate, maintaining a balanced and objective tone throughout. The cyclic universe theory isn't just a scientific theory, but a profound idea that challenges our perception of time and existence.